And there we are. We're live. We're taping. So, talking about the air. We've talked a lot about air. Another thing is stability. And this has a lot to do with humidity and this idea of expansion contraction. So, the adiabatic process is this. As air rises, so a piece of air, right, a parcel of air, as it rises, it expands. And that's because air pressure, right? We talked about air pressure before, that the further you go from the surface, the less air pressure there is. So as air rises, it expands. There's less air to squeeze it together. And as it expands, it cools. That's the adiabatic process. Um, these are actually hot air balloons. This is a festival in Albuquerque. And a hot air balloon is quite simply this. Hot air wants to rise. And so if you take a balloon that holds the air inside of it and you burn something under it, like a fire, to heat it up, this air is hotter than the air around it. It's going to want to rise. Interesting little note. This may not be something you've noticed. I didn't know this one. If you ever take a bag of potato chips and you go in altitude, so go up in the mountains or on an airplane, sometimes they'll actually puff out or explode, because what happens is when this is bagged, say in Chicago at 500 feet above sea level, and it's bagged as air pressure, it's fine. But if you go up to Denver, which is 5,000 feet above sea level, so that's a 1,400 feet difference. The air pressure is so less that the air pressure inside that bag was bagged at a higher pressure. It actually pushes out. It's a weird thing. But this leads to two things that affect weather. Adiabatic temperature changes, cooling. So air is cooled or warmed. As air expands, right, warm air wants to rise because warm air has more energy, and warm air expands, it wants to rise. But as it expands, that very act of expansion cools the air, so it loses its heat. Conversely, air that is pushed down or is compressed or squeezed, and if you move air down to the surface, air pressure pushes it, air that is compressed warms. So I've got this little graphic. Maybe this will work. Imagine here you've got this cylinder of air. So these are molecules of air, oxygen, carbon, whatever. And I've got this vast cylinder, and I'm going to squeeze it. Now watch right here. They're bouncing around. As I squeeze it, they start bouncing faster because there's less place to bounce. They bounce off each other. So they bounce faster. Right? Now they're really fast. Now watch, I'm going to go back. I'm going to give them more space. So now they can stop bouncing off each other. They stop bouncing quite as much because now they don't ricochet off each other, and they start going slower. And as I squeeze it again, they're going to start going faster. So as you compress something, the molecules move faster because they bounce off each other because they're closer. Well, remember we talked about that. Heat is molecular movement. So if the molecular movement decreases like it is here, then the temperature drops. That's adiabatic cooling. If air is compressed, right, then the movement increases and temperature increases. So this process is a big factor that drives weather. And here's an example. Here you have a bright sunny day. You've got this parcel of air right here near the ground, and the sun's heating on it so that it warms up. So as the air warms, it rises. But as it rises, it expands. And so it goes from 86 degrees here to up at 1,000 feet. Now it's doubled in size, but now it's down to 68 degrees. And if it keeps on rising, and here it's even bigger, now it's only 50 degrees. So as the air rises, it expands and cools. And then conversely, if something happens to drive this air downward, and we'll talk about that, it's compressed. And as it gets compressed, it warms. Now that is what we call the adiabatic rate. So the first one is the dry rate. And this is, you don't have to know the formula, so don't get out the calculators, don't worry about that. What the dry adiabatic rate just says is that there is a mathematical model that predicts how fast temperature will change based on elevation. So for example, if you go for every 1,000 feet, a parcel of air will drop 5.5 degrees. So that being said, you could measure the temperature at the surface, and say you're at sea level and the temperature is 55 degrees. Well, you know that if you go up 1,000 feet, it'll be 50 degrees. And if you go up 2,000 feet, it'll be 45 degrees. That's what that means. That's called also the environmental lapse rate, right? So you don't need to know the actual numbers. Just know that there is a rate, and it is affected by water. We'll talk about that. That's the dry rate. The moist rate is different. And the moist rate, or basically the rate at which air cools as we go up, if there's a difference, moist rate is always less. In other words, the more moisture in the air, the slower the air cools as it rises. These act to form the LCL. So basically this, right? We know that as air rises, it's going to expand and cool. We've also just learned that as air cools, it becomes saturated. And at a certain point, when air gets too cold, it can't hold any water. And if it continues to get cold, any water that is liquid will be turned back into what? Liquid, right? So if air has water vapor in it, and it cools and cools and cools, and usually it cools because it's lifted, at a certain altitude above the earth, right? That water vapor as a gas will be turned back into water as a liquid. And that is called the LCL. In other words, this is the altitude at which the temperature of the atmosphere goes below the dew point. Any water that is vapor will turn into clouds. So, and what additionally happens is because you do that, you have that idea of latent heat, that energy boost at the change level, right? So then the cooling slows down even further, and this allows clouds to grow. So the LCL is where clouds form. Here's a picture. Here's an island in the Pacific Ocean, clear skies, but you've got warm, moist air blowing over the ocean. It comes into this island, and it hits the island, and it blows up the hill. And as it goes up in altitude, at a certain point, and this point is this imaginary line, the air has cooled to the point where all the moisture is condensated out, turns back into water, and clouds form. And again, these are just millions of drops of water just floating. So clouds always form at the LCL. Below this level, the air can hold water as a gas. Above it, it cannot. And what determines this height? Many factors. Here's another kind of representation, right? As air is going up, as it moves up, it's cooling, and the LCL right here is at 2,000 feet for whatever reason. At 2,000 feet, the air temperature is such that the air condensates out. And now the rate of cooling continues, but it continues at a little bit faster rate to finally the point where all the moisture is driven out. Adiabatic cooling leads to this idea of atmospheric stability. I know I keep on throwing these concepts and terms at you, but these are all going to build so that we can see how weather actually happens. Stable atmosphere. This just means this. The conditions are such that the air will basically stay the same. It doesn't rise or fall unless something else happens to make it. All things being equal, the air is going to stay where it is. So then obviously if you have an unstable atmosphere, something is happening. The conditions are that the air is not stable. Some will rise and fall. So this is a little bit complicated. I'm going to hopefully get this to you in an image. So let's talk about it. A stable atmosphere. A stable atmosphere is this. That here is the air temperature at ground level. 30 degrees, 18, 6 degrees, -6 as we go up. If the conditions are that this parcel of air, it may be the same temperature. But as it goes up, if the dry adiabatic rate lets it stay the same, even though it's a little bit warmer than this, it's not too much. So it's not going to rise too much. It's pretty much going to stay here because there's nothing to drive it up. In other words, the rate of cooling for this air parcel is the same as the rate of cooling for temperature outside the air parcel. And that's the case. If these two rates of cooling for regular air and these different temperature airs is the same, then they're going to pretty much stay there. This is pretty much going to stay in this area. Air is going to be stable, no wind. So sorry, right here. But what happens if there's a difference? If the air in these pockets cools at a faster rate or a slower rate than this, that's going to cause these air packets to either rise faster or slower than the regular air. And this is when you get turbulent, unstable air. This is generally when we start having weather patterns like beyond clear skies happen. A thunderstorm is a great example of this. A thunderstorm is the result of different conditions, wind and humidity and heat, that form this situation where the air may be stable for the most part here at the ground level, but above ground, very unstable. And there's a lot of turbulence and a lot of mixing and a lot of movement. And that movement adds more energy. That's why I'm doing this, kind of give you the idea of energy to thunderstorms or hurricanes or tornadoes. I'm going to pause right here for station identification. Time for us to all get up and shake out the sillies, get all that good stuff going. In my case, maybe a throat drop, a lozenge. Try to figure out why this video is locking up, and we'll come back in just a little bit.